Hello there, and welcome. Tonight, we'll explore something so large, so staggeringly vast, that even light, the fastest thing we know, takes eons to travel across it. The universe isn't just big, it's beyond. Galaxies the size of cities vanish into specks. Time stretches, warps, and slows, and somewhere, quietly orbiting a warm yellow star, we sit trying to picture a scale we were never meant to grasp. But what if we tried? Tonight, you'll hear 100 facts about the size of the universe that might just change the way you look at everything, including yourself. Not in a loud, overwhelming way, but softly, steadily, like gravity shaping a planet over time. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. Light is fast, the fastest thing there is, as far as we know. It moves at 299,792 kilometers per second, slicing through the vacuum of space like a silent blade. It's so fast that it can circle the Earth 7 times in a single second. And yet, in the face of the universe, light begins to feel slow, lethargic, even, as if it's trying to keep pace with something far too large and falling a little further behind with every second that passes. The light from our sun takes just over 8 minutes to reach Earth. That means everything you see when you look at the sun through proper protection, of course, is already 8 minutes old. If the sun vanished this very instant, the sky would remain bright for those final 8 oblivious moments. Every sunrise is a memory. Every ray is a fragment of the past, arriving on schedule. But 8 minutes is nothing. The light from the nearest star beyond our sun, Proxima Centauri, takes over 4 years to get here, which means if something happened there right now, a flare, an explosion, the birth of a planet, we won't see it until 2029. It's as if space has a built-in delay, a cosmic buffer that reminds us how small and how late we are to the party. Beyond that, light from the Andromeda Galaxy has been traveling for 2.5 million years to reach your eyes. That dim smudge in the night sky, that ghost of a spiral drifting above the horizon, shows you what Andromeda looked like long before humans had learned to write. Before we tamed fire, before our species even existed in its current form, you are not seeing Andromeda. You are seeing its ancient self. Andromeda is close, relatively speaking, just next door, cosmically. But if you reach farther, much farther, you begin to see the shape of something truly impossible. The observable universe is around 93 billion light-years across. That number already feels too big to grasp. But here's where it becomes strange. The universe itself is only 13.8 billion years old. So how, then, can we see 93 billion light-years out? It's because space itself is not just full of things, it's stretching. The fabric of the cosmos is expanding, not into something, but of itself. As light travels, the universe expands underneath it, pulling galaxies ever farther apart. So the photons that left ancient galaxies billions of years ago have been stretched too lengthened, like taffy in a machine that never stops turning. This means we are seeing objects whose light began traveling when the universe was much younger. But those objects are now much farther away than where they started. They're still visible, but only because their light left so long ago. Many may no longer exist. The image lingers, but the thing it came from may be gone. You're not seeing the universe as it is. You're seeing a slideshow of what it used to be. Beyond your room, beyond your window, nothing is happening right now in any meaningful way. The stars you see twinkle from the past. The galaxies you admire in photographs are frozen versions of themselves, preserved not by choice, but by the limits of light itself. Even the moon, just a stone's throw away, shows you its face with a delay of 1.3 seconds. We've never seen the universe in real time, not even once. In that sense, you live inside a kind of time machine. Every glance at the sky is a look backward. Every beam of starlight that touches your skin is a message sent before you were ready to receive it. The night sky is not a place, it's a history. And the further out you look, the older the story becomes. The cosmic microwave background, the oldest light we can observe, is about 13.8 billion years old. It's not light in the way we normally see. It's been redshifted down to microwaves, stretched across space and time until it became faint static. But that static is a whisper from the Big Bang, a flash of light from the moment the universe cooled enough for atoms to form. Before that, light couldn't travel at all. The cosmos was a soup of particles too hot and too dense for photons to roam free. There was no sky, no stars, only a glowing fog. So the light we see from that time is the edge, not the edge of the universe itself, but the edge of what we can ever see. Beyond it, there is more. More stars, more galaxies, possibly even an infinite stretch of space. But no matter how long we wait, no matter how powerful our telescopes become, that light will never reach us. It's traveling, yes, but the space between us is expanding faster than light can close the gap. Some parts of the universe are retreating faster than light, not because they're breaking a speed limit, but because space itself is swelling beneath them. And in that expansion, we lose sight of them not just visually, but permanently. They slip beyond the cosmic horizon, not behind a curtain, but into silence. This means there are galaxies out there, spinning and evolving, whose light will never reach us. They exist, they shine, they age, and they do so entirely unobserved. Not because we aren't looking, but because we can't. Their stories unfold in a sealed book, with pages we'll never turn. What we call the observable universe is not the whole. It's just the part of the universe that has had time to speak to us. And even that portion is mind-breaking. If you wanted to travel across it, you'd need to move at the speed of light for 93 billion years, and that's only one direction. But that's not the most difficult part to grasp. The most difficult part is this. Even the light you see from your own past, the galaxies you study, the cosmic background you analyze, is still only a glimpse, a sliver, a blink. There is no full picture, no true map. The universe is too big to fit inside any single moment. And yet here you are, nestled on a small world, wrapped in the atmosphere of a blue planet, receiving photons from every direction. You are catching stories millions or billions of years in the making. They reach you not in books or words, but in light. You don't just live in the universe, you are lit by it. Every shadow you cast during the day, every glimmer you see at night, is shaped by a journey that began long ago and far away. And no matter how far we look, how deep we reach, there will always be more we can't see. Because even light, the fastest thing we know, cannot outrun the vastness it's trying to reveal. Earth feels big when you're standing on it. The oceans seem endless. The horizon curves with quiet authority. Mountains rise like monuments. But step outside our atmosphere, just once, and the illusion begins to crumble. Earth is not large, not in cosmic terms. It is a grain, a whisper, a faint warmth orbiting an ordinary star. Take Jupiter, the gas giant, king of our solar system. It doesn't just dwarf Earth, it swallows it whole. Over 1,300 Earths could fit inside Jupiter's volume. Its mass is so great that it doesn't orbit the sun in the same way the other planets do. Instead, the center of mass between Jupiter and the sun lies just above the sun's surface, a subtle tug that shifts the balance of the entire system. Jupiter is a planet, Yes, but also something just shy of a star. If it were 80 times more massive, it could have ignited. And then there are the planets we've never seen up close. Exoplanets, worlds orbiting stars far from our own, are not just common, they're diverse in ways we didn't expect. Some are bloated giants, larger than Jupiter, so puffed up by heat that their atmospheres stretch like balloons. Others are compact but heavy, made almost entirely of metal or ice. There are super-Earths, mini-Neptunes, hot Jupiters, and planets with rings so vast they would eclipse their own stars if viewed from the right angle. But size alone isn't what makes them staggering. It's the systems they live in. Some planetary systems are so wide that their outermost planets take centuries to orbit. The span from one end to the other can stretch across light hours. That means light, moving at its unthinkable speed, would still take hours just to cross the space from one sibling planet to another. Imagine a solar system so vast that sunrise and sunset happen in entirely different decades. This isn't fiction, it's observation, it's real. And then there are the planets that don't orbit anything at all. Rogue planets. These are the wanderers, massive worlds flung free from their stars, drifting through the galaxy in eternal night. Some are larger than Jupiter. Some may be as small as Earth. All of them are alone, without sunrises or seasons, moving silently between the stars. They could number in the billions. They might even outnumber the stars themselves. They do not shine. They do not glow. They are almost invisible, found only through the faint tug of their gravity or the ghostly glow of heat left over from their formation. If one passed close to our solar system, we might never see it coming, just a slow, heavy presence, slipping by in the dark. But not all massive objects are planets. Some stars are so enormous they bend our idea of what a star even is. Take UY Scuti, one of the largest known stars by radius. If placed at the center of our solar system, its surface would reach past the orbit of Jupiter and possibly Saturn. It is not dense, but sprawling. Its outer layers are thin, stretched by radiation and time, and yet it burns, a bloated, dying sun in the final chapters of its life, shedding mass, fading slowly. Stars like this defy scale. They make even Jupiter feel small. In some systems, these giants are orbited by planets that in turn are larger than any we've found. A dance of enormous bodies around an even larger partner. Systems where size stacks upon size until the human imagination begins to buckle under the weight of what it's trying to hold. Here on Earth, we measure things in kilometers, in hours, in familiar units shaped by our own biology. But the universe doesn't care about what's familiar. It builds on a scale we were never designed to witness. And yet we try. Through telescopes, through data, through drifting signals gathered from stars that have never seen our sun, we learn of planets that could hold thousands of Earths, of solar systems so wide they blur into starlight, of worlds that drift with no sun, no orbit, and no name. And we realize, with quiet awe, that our planet is not the rule, it is the exception. A small, balanced place in a universe of giants. On a clear night, far from city lights, you can look up and see a streak of white mist stretched across the sky. It glows softly, like breath on glass, a quiet arc rising from horizon to horizon. That's the Milky Way, or at least, the part of it you can see, the part our atmosphere allows, that our eyes can catch, that isn't drowned by the light of our own making. It's beautiful, haunting, and immense, but it's a trickle, just the faintest drop from a cosmic ocean. The Milky Way is not a line in the sky. It is a galaxy, a sprawling disk of stars, dust, gas, dark matter, and memory so wide that even light takes 100,000 years to cross it from end to end. It spins slowly, like a great wheel in space, carrying with it hundreds of billions of stars and untold planets. And tucked away, orbiting quietly in one of its many spiral arms, is a small yellow star we call the Sun, with Earth clinging to it like a child gripping a parent's hand in a crowd. We are part of the galaxy, but we've never truly seen it. The fraction of the Milky Way visible to the naked eye is almost comically small, less than 0.00003%. That's not even a slice. It's a glimmer, a hint. Imagine being inside a vast cathedral, one so enormous its walls curve into darkness. Now imagine trying to understand the shape of that cathedral by looking at a single stained glass window near the door. That's our view of the Milky Way. From within the galaxy, we can't step back and look at it. We are embedded in it, like a single cell trying to map the whole body. Even the brightest stars we see at night, those that seem just within reach, are usually dozens, hundreds, sometimes thousands of light years away. Most are not nearby at all. They just burn with enough heat and force to cut through the fog of distance. Many are giants, some are dying, others have already died, and we are only just now receiving their final light. And while we look up, wondering how far those stars might be, we are moving. The Earth is not still. It spins on its axis, orbits the Sun, and the Sun, in turn, is dragged along by the Milky Way's rotation. We are in motion constantly, silently. Our entire solar system is completing a slow, vast circle around the center of the galaxy. But this orbit is no quick loop. One full trip around the Milky Way takes about 250 million years. That means Earth has only made around 20 trips since it first formed. The last time we were in this same spot in the galaxy, the dinosaurs were just beginning to walk. The continents were in different places. The oceans held different life. The sky may have looked nearly the same, but the planet beneath it was alien. Our solar system is like a horse on a cosmic carousel, riding the edge of a galaxy that moves too slowly for any lifetime to feel. And yet, that movement is constant. We are always drifting, always shifting, always circling something we can't quite see. At the heart of the Milky Way lies a mystery, a black hole, massive and quiet, called Sagittarius A*. It's not the devouring monster of fiction, not a swirling mouth of chaos, but a steady gravitational anchor around which the entire galaxy turns. We don't see it directly. We feel its pull. Like a dancer spinning around a partner who never steps into the spotlight, every star orbits something in the dark. And still, with all of this motion and complexity, the Milky Way is just one galaxy among billions. From Earth, it dominates the sky, not because it is the only one, but because we are inside it. If you could travel far enough away, you might look back and see it as a glowing pinwheel, one among many. But here, from our limited perch, it appears not as a whole, but as a texture, a smear of starlight across the night. Even when you photograph it, capturing long exposures with sensitive cameras, what you see is only part of the story. Much of the Milky Way is hidden by clouds of dust, enormous dark regions where light from distant stars is absorbed and scattered. These gaps are not empty. They're full of material hydrogen, carbon, molecules that might one day become planets or people. But to the eye, they're voids, shadows painted onto the sky. It's humbling, really, to know we live inside something so vast and vibrant, and yet experience only the faintest whisper of it. The stars you see tonight are not a crowd gathered around you. They are beacons scattered across a colossal plain, each burning its own age, each telling its own story. And they are only the closest, the brightest, the most persistent. The galaxy hides more than it reveals. You've never truly seen the Milky Way. Not the way it is, not the way it moves or breathes. You've seen its edge, its glow, its illusion. But the rest of it, the hundreds of billions of stars, the silent orbits, the spiral arms twisting through dark space, those remain out of reach. Not because we aren't looking, but because even here, from inside its heart, the Milky Way is too large to hold in the mind all at once. And maybe that's the point. Maybe some things are meant to be felt more than seen. The sense of motion beneath your feet. The light of a star that left its home before your species had a name. The understanding that the night sky is not a ceiling, but a window, and through it, we are watching the galaxy as passengers, not observers, still spinning, still orbiting, still trying to see the thing we are already inside. Time, for most of us, feels like a steady river. It moves in one direction, at one speed, unchanging and familiar. A second is always a second. An hour always ticks by with the same rhythm. But this comfort is an illusion held together by gravity, velocity, and proximity. Step away from Earth, venture far enough or fast enough, and time itself begins to stretch and bend like warm glass. Einstein showed us that time and space are not separate. They are stitched together into a single fabric, space-time. And this fabric is not flat. It bends under the weight of mass. The heavier something is, the more it curves the space around it, and the more it bends time. It's called gravitational time dilation, and it means that the deeper you are in a gravity well, the closer you are to a massive object, the slower time moves for you compared to someone farther away. On Earth, the effect is subtle. A clock on the ground floor of a skyscraper ticks ever so slightly more slowly than one at the top. GPS satellites have to account for this distortion, otherwise our navigation systems would drift and collapse. But move beyond Earth's grasp, and the differences become dramatic. Imagine orbiting a black hole, not plunging into it, just hovering near its edge, dancing along the event horizon. From your perspective, time feels normal. Your heartbeat keeps its rhythm. You blink, you breathe. But to an observer far away, watching from a safe distance, everything about you slows, each movement stretches, seconds become minutes, minutes become years. If you stayed long enough and then left, you could return to find that entire centuries have passed in the universe beyond, while only hours passed for you. Your seconds are not the same as someone else's. This isn't theory anymore. We've seen it in action. The gravity probe missions, the twin astronaut experiments, atomic clocks flown on planes or carried up mountains. All of them confirm that time flows differently depending on where you are and how fast you're moving. It's not a metaphor or a trick of the mind. It's measurable. Time itself bends under weight, and the most extreme bending happens near black holes. These are not holes in the traditional sense. They are points of collapse, where matter has been crushed into a space so small that nothing, not even light, can escape. Around them is the event horizon, the boundary between where escape is still possible and where it no longer is. Cross that threshold, and you fall inward forever. But just outside it, time becomes strange. A second near the edge might be hours or days to someone farther out. The pull of gravity is so intense that even the flow of time is slowed, as if the clock itself is gasping for breath. If you dropped a watch toward a black hole, it wouldn't just fall. From your perspective, watching from a safe distance, it would seem to slow down. It would spiral inward, its ticks growing farther apart. Just before it reached the event horizon, it would appear to freeze, its final moment stretched out infinitely, not because it stopped, but because your time and its time had drifted so far apart they could no longer touch. Now consider this. There are regions in the universe so dense, so warped, that their gravitational time dilation would be impossible for us to comprehend. In some places, a single second could stretch into hours. If you could somehow exist there and then leave, returning to Earth, you might find that everyone you knew had grown old or vanished. Civilizations could rise and fall while you felt only a long breath. And the reverse is also true. Travel fast enough near the speed of light, and your time slows as well. Not in your body, but in comparison to everything else. You could fly across a galaxy, watching the stars slip by like headlights on a dark road, and when you came back, millennia could have passed while you aged only slightly. In this way, space is not just wide, it's elastic. It's sculpted not only by mass, but by motion. Move fast, fall deep, stretch far, and the clock will change its tune. We tend to think of time as a ruler, straight, consistent, but in the universe, time is more like a landscape. It has valleys and peaks, plateaus and cliffs. A black hole is a canyon in time. A fast-moving ship is a slope. Two people can start at the same moment and end at very different places, depending on how they travel and where they go. And yet, to each of them, time feels normal. That's the trick. You never feel the change. Time does not whisper that it's slowing down. Your heartbeat stays the same. Your thoughts don't lag. But the universe sees something else. The universe keeps both times, both truths, both paths. 1 second here might be an eternity there, and so we live our lives, moving through a universe where clocks do not agree, where time bends like light, curving around mass and motion, where a moment can be stretched, where a life can pass unnoticed, where now is not the same everywhere. And as you lie still, listening, breathing, existing, your body held gently by Earth's own pull, time, for you, ticks forward at its own pace. But somewhere else, near a silent black horizon or inside a speeding ship, someone else's second is refusing to match yours. Their clock hesitates, yours runs on. This is the quiet truth of the cosmos. Time is not fixed. It flows, and sometimes it folds. Imagine holding out your hand, palm open, and placing a single grain of sand on your fingertip. Something so small it barely has weight. A fleck of mineral, shaped by tides and time. Now stretch out your arm, lift that grain to the sky, and imagine looking through it right through the spot it covers in the heavens. That's what the Hubble Space Telescope did. For weeks, it stared into what appeared to be a perfectly empty patch of sky, dark, vacant, silent. A piece of the cosmos no bigger than a grain of sand held at arm's length. There were no bright stars there, no nearby galaxies to dazzle the lens. Just blackness, a cosmic blank page. But Hubble kept watching, exposure after exposure, hour after hour. And what it revealed was not emptiness, but abundance. Thousands of galaxies, spirals, ellipticals, irregular clusters, and glowing smudges of ancient light, each containing billions, sometimes trillions, of stars. And this was just one minuscule fraction of the sky, one pinpoint in a universe full of them. Multiply that image across the entire night sky, and the numbers swell past comprehension. We now estimate that there are around 2 trillion galaxies in the observable universe. That word trillion feels heavy, but even it buckles under the scale we're discussing. 1 trillion seconds ago, there were no pyramids. 1 trillion drops of water couldn't fill an ocean. And yet, when we look outward, that number becomes almost mundane. 2 trillion galaxies, each teeming with stars, planets, gas, dust, mystery, each one drifting through space on its own journey, shaped by time, gravity, and collisions stretching back billions of years. And these are only the galaxies we can observe. Beyond the edge of what light has had time to reach us since the beginning of the universe, there may be more, many more too distant for even our most sensitive instruments. Their light is still in transit, still moving through the dark, on a path that may never end at our eyes. We are surrounded by what we cannot see. Most galaxies are invisible to us, not just because they are far, but because they are faint. Some are shrouded in dust, hidden behind other objects, or simply too small and dim to register against the backdrop of cosmic noise. And yet, they exist. They spin. They collide. They form stars and harbor planets. They live out their lifespans in silence, whether or not anyone is watching. Even the galaxies we can see don't always appear as they are. Because light takes time to travel, looking outward is also looking backward. When we see a galaxy 1 billion light years away, we are seeing it as it was 1 billion years ago. Its current state, its stars, its shape, its fate remains unknown to us, hidden by the sheer distance between us and the truth. In this way, The universe is a time machine, a scattered mosaic of moments, all arriving at once, layered across the sky. Some galaxies are just beginning to form, glowing faintly in the far reaches of the visible field. Others are ancient giants, nearing the end of their cosmic evolution. There are galaxies in clusters, drawn together like dancers in an infinite waltz, and galaxies drifting alone, flung outward by past collisions, destined to wander. The vast majority of stars in the universe live in these distant realms, never seen, never named. For every star you see twinkling above you, there are billions more hidden in galaxies so far away they appear as nothing more than static. Light from those stars has crossed oceans of time to get here. Some began their journey when Earth was molten, others when the first plants took root, still others when humans were just learning how to shape tools. And all of it, every star, every galaxy, every wisp of dust and gas is carried within this thin sphere we call the observable universe, a boundary not of the universe's true edge, but of light's reach. We don't know what lies beyond. We may never know. The universe could be infinite. It could curve back on itself, or it could be one of many, an island in a sea of others. But here, in our one sky, on our one world, we stare upward and glimpse the truth that what we call space is not empty. It is saturated with structure, layered with depth, overflowing with galaxies like grains of sand scattered on a beach, each one a cathedral of stars, each star a furnace of fusion, each planet a potential story unfolding in darkness. And through all this, we drift quiet, small, aware, a single point of consciousness among countless galaxies caught between wonder and distance. The night sky is not just beautiful, it is crowded. But only if you know how to look. If you could zoom out far enough, far beyond the clouds, past the pull of Earth's gravity, beyond the sun's domain and the quiet edge of our solar system, you'd find that the stars begin to thin. The planets vanish behind you. Even the Milky Way, with all its spirals and shimmer, fades into a single glowing thread, curving gently in space, and beyond that, the darkness deepens again, scattered not with stars but with galaxies, hundreds of billions of them, drifting slowly, almost imperceptibly, like dandelion seeds carried on a breeze you cannot feel. They are not frozen, they move. Each galaxy, massive and immense, slides through space like a whisper. Some spin, some tumble, some stretch as they go, distorted by unseen forces. And some, like ours, are heading straight toward another. The Andromeda Galaxy, our nearest large neighbor, is on a collision course with the Milky Way. It is 2.5 million light-years away, which feels like safety, but it's closing that gap every second. Right now, as you lie still and breathe, it approaches us at 110 kilometers per second. That's fast enough to cross an ocean in less time than it takes to blink. And yet, because the distances are so vast, the meeting won't happen for another 4 billion years, but it will happen. The two galaxies will collide, pulled together by gravity's quiet hand. It won't be sudden. There won't be an explosion or a crash in the way we imagine. No sound, no fire, just a long, slow dance of attraction. A gravitational spiral where arms stretch and tangle, stars shift, and the shapes we know are erased and rewritten. Over hundreds of millions of years, the Milky Way and Andromeda will pass through each other, again and again, like ghosts learning to share the same room. And despite the drama of the moment, the stars themselves will almost never collide. It seems impossible. How can something so large smash into something just as massive and yet not break into pieces? But galaxies are mostly empty space. Even in the dense core of a spiral arm, stars are separated by trillions of kilometers. If our sun were the size of a coin, the next nearest star would be another coin placed hundreds of miles away. The odds of two stars hitting head-on during a galactic collision are vanishingly small. Instead, what changes is the structure, the shape, the momentum. Gravity reaches across the void and begins to sculpt something new. Galaxies twist and stretch. Some stars are flung outward, exiled into the intergalactic dark. Others fall inward, drawn to the swelling core of the new merged galaxy. Gas clouds collide, sparking waves of star formation, new suns lighting up in the aftermath like embers from a distant fire. In the chaos, beauty is made. Eventually, what remains is not the Milky Way, not Andromeda, but a single, larger galaxy rounder, quieter, stranger. It will likely be an elliptical galaxy, smooth and featureless from a distance. The spiral arms will have been stretched and torn beyond recognition. The names we gave those shapes will no longer matter. It will have a new name, maybe one our descendants will choose, if any still exist, to witness it. And within it, the sun, if it hasn't burned out by then, may still circle quietly, just one star among hundreds of billions in a galaxy born from motion and time. Galactic collisions are not rare. They are how galaxies grow. They merge, absorb, expand. Even now, in distant corners of the universe, telescopes catch glimpses of galaxies mid-embrace, twisting into new forms, lighting up with newborn stars, stretching trails of gas and light, like threads pulled loose from a tapestry. The universe builds its largest structures, not with speed or violence, but with slow, persistent pull. One whisper drifting into another. Sometimes, a small galaxy brushes past a larger one and is devoured entirely. Its stars are absorbed, its shape erased. Other times, galaxies of similar size meet head-on and forge something together. It's a strange kind of death, and a stranger kind of birth. And all the while, stars go on burning. Planets continue to orbit. Life, if it exists, remains unaware. We think of space as still, but in reality, it's always shifting. Galaxies move through, dark matter like ships through an invisible ocean. They follow the contours of cosmic filaments, pulled toward dense regions, away from voids. Gravity tugs at them from every direction, and over billions of years, their paths curve, converge, and entwine. We live inside one of these quiet travelers, a single galaxy on a slow-motion collision course that won't be finished for another few billion years. We won't be here to see it, but it's already happening. The whisper has already begun. If you could step outside the universe just for a moment, just far enough to look back and see it whole, you wouldn't see galaxies scattered at random, like glitter thrown across black velvet. You wouldn't see chaos. You'd see something far stranger. You'd see a pattern. It's faint, subtle, almost hidden beneath the surface of things, but it's there. The cosmos is not uniform. Galaxies aren't spread evenly like dots on a grid. They clump and curve, drawn together by gravity, shaped by time, forming structures so immense that even light struggles to cross them. They cluster into groups, those groups into clusters, and those clusters into something bigger, still superclusters, arranged in threads that span the heavens like spider silk drawn across infinity. These are cosmic filaments, the great scaffolding of the universe, invisible to the eye, yet mapped by the movements of galaxies and the whispers of ancient light. They stretch for billions of light years, like roads between cities, carrying matter along their lengths, guiding the birth of stars and the growth of galaxies. They frame the shape of everything, and in the spaces between them are the voids, immense regions of emptiness, dark and almost entirely devoid of stars. The filaments and the voids together form a kind of web, a cosmic lacework. It is sometimes called the cosmic web, but web is too fragile a word. It is a skeleton, a frame, a ghostly map of creation, and among these filaments is something even more staggering. In 2013, astronomers peered deep into the sky and found a wall. Not a wall like brick and stone, but a structure something vast and cohesive and impossibly large. They called it the Hercules Corona Borealis Great Wall. It stretches across more than 10 billion light-years of space. 10 billion. That's more than 2/3 the length of the observable universe. If you started on one end and traveled at the speed of light, you'd still be moving 10 billion years later, and you still wouldn't reach the far side. It is, as far as we know, the largest single structure in the universe, and it shouldn't exist. According to our current understanding of cosmology, structures that large aren't supposed to form. The universe hasn't had enough time to allow matter to clump together at that scale, not without violating the assumptions baked into our most trusted equations. And yet, there it is, a great, glowing thread of galaxies and clusters and gravity stitched into the sky, defying what we thought we knew. It's so big that light from its farthest end began its journey not long after the Big Bang. When you look at the night sky, you see stars. When telescopes look deeper, they see galaxies. But beneath that is a hidden pattern, an architecture of connection. Clusters that bend toward one another, gravity wells tugging on ancient starlight, the dark matter that binds it all, unseen and yet essential, like mortar between bricks. Everything drawn together by a force that moves slowly, but never stops moving. Our own Milky Way galaxy lives inside a small filament, tucked inside the Laniakea supercluster, which itself is just a minor thread in this enormous weave. We are not at the center of anything. We are not even on the edge of anything. We are a point within a point, a swirl inside a swirl, floating within a structure so large that calling it big doesn't mean anything at all. And yet we're part of it. Our atoms, our breath, our orbit, our light, all of it belongs to this quiet scaffolding. Everything we are is embedded in a pattern that reaches beyond imagination. When we map the cosmos, we are not just making charts. We are finding our place in a structure too vast to touch, too slow to notice, too distant to feel, and yet utterly, completely real. These structures are still forming. Even now, galaxies drift along the filaments like dust caught in a current. Superclusters bend toward one another. The cosmic web tightens, ever so slightly, under the pull of dark energy and dark matter. It is a slow collapse, one that takes billions of years to unfold. The universe is not static. It is always becoming something else. And the strangest part is this: we can see it. We've built instruments that trace microwave radiation from the birth of time. We've charted the positions of 1 million galaxies and use them to draw invisible lines between the visible things. And when we do, we see that the universe is not chaos. It is shape, form, connection, an ancient geometry etched in the dark, all of it moving, breathing, expanding. Sometimes we imagine ourselves as small, and in many ways we are. But there is something profound in knowing that we are part of a pattern this vast, that your life, your thoughts, your breath is happening in a galaxy that is orbiting inside a cluster, which is falling toward a supercluster, which is stitched into a filament, which is woven into a wall 10 billion light years wide. And somehow, we're able to know that, to sense the whisper of structure in the noise of stars, to find the thread and follow it home. Somewhere in the center of our galaxy, past the spiral arms and drifting dust, beyond the constellations and clouds of gas, there is something waiting. It doesn't glow. It doesn't spin in the way we can see. It doesn't shout its presence into the sky. But it holds the entire heart of the Milky Way in place. Its name is Sagittarius, A*, and it's a black hole. 4 million times the mass of our sun, squeezed into a space smaller than the orbit of Mercury. Not an object, exactly, but a region of space-time where gravity folds inward on itself so completely that not even light can escape. It is not just dense, it is a point beyond understanding, where space and time twist into silence. And it's not alone. Scattered across the cosmos are other black holes, some the remnants of stars, others titanic anchors in the hearts of galaxies. A stellar black hole might weigh as much as 20 suns, but be no larger than a city. You could drive around its circumference in a few hours if you had a road that could survive gravity strong enough to shred atoms. These are born when massive stars collapse in on themselves, their fuel spent, their cores imploding with such force that the laws of physics themselves surrender. But as black holes feed on gas, on dust, on unlucky stars that wander too close, they grow, and over time, they can become monstrous. Ultramassive black holes exist, and they are among the most mysterious structures in the universe. Some are 10 billion times more massive than the Sun. One, known as Ton 618, weighs over 66 billion solar masses. It's hard to make that number mean something. You could drop every planet, every star, every piece of matter in the Milky Way into it, and it would barely notice. It would not hiccup. It would not glow. It would simply continue being what it is, a hole in the fabric of everything. But black holes don't just sit quietly. In some ways, they shape the galaxies that host them. A black hole doesn't have to touch something to influence it. Its gravity extends far beyond its visible edge. Gas clouds spiral into its mouth in great disks, heating up as they fall, glowing brighter than entire galaxies as they scream toward the event horizon. These disks can blast radiation and matter outward in colossal jets that stretch thousands of light years, sculpting the space around them, triggering the birth of stars in some places and snuffing it out in others. It's a paradox, an engine of destruction that also creates. Galaxies are not passive around these giants. The central black hole and the stars around it interact in strange and intimate ways. The more massive the black hole, the more massive the central bulge of the galaxy tends to be. It's as if the two grew up together, co-evolving, influencing each other over billions of years. The galaxy feeds the black hole, and the black hole, in turn, shapes the galaxy's destiny. And yet, black holes remain hidden. You cannot see them directly. You cannot watch them spin. But we know they're there because of how they affect the world around them. Stars orbit invisible centers. Gas disappears into emptiness. Time itself slows at their edges. They warp everything near them, not just physically, but mathematically. They're like punctuation in the sentence of the universe, marks of finality, where logic bends and something else begins. If you were to fall into one, you wouldn't feel much at first. Assuming it's a supermassive black hole and not a stellar one, the gradient of gravity might be gentle enough that you'd pass the event horizon without noticing. But beyond that point, escape is impossible. Not because something would pull you back, but because the very shape of space no longer allows an outward path. It would be like trying to walk uphill in a world where up no longer exists. And deeper still, there is a mystery. At the heart of every black hole is a singularity, or so we think, a point where density becomes infinite and our understanding of physics breaks down completely. General relativity stops working. Quantum mechanics can't cope. It's as if the universe has pulled a curtain across this region and whispered, "Not yet." Some physicists believe that black holes may not be the end of a thing, but the beginning of something else. Wormholes, baby universes, a portal to somewhere we can't even describe. These aren't confirmed theories, they're questions. But black holes invite questions like no other object in the cosmos. They consume, but they don't vanish. They grow. They anchor galaxies. They bend light. They stop time. They challenge everything we thought we knew about space and existence. And for all their strangeness, they are real. Not rare, not theoretical, but out there, millions of them waiting quietly in the dark, pulling at the fabric of reality with a hunger that never sleeps. The universe is expanding, cooling, growing older. But black holes, they stay. They last. When the stars have gone cold and the galaxies are dust, the black holes may still be here, silent and vast, holding the memory of everything they've taken, watching a universe that can no longer watch back. The night sky looks still. If you step outside on a clear evening and stare upward, the stars seem fixed in place, calm and eternal. The same constellations return each season. The same soft band of the Milky Way arches across the darkness. It feels timeless, unchanging. But this stillness is an illusion, because the universe is not resting, it's growing. Not just the galaxies drifting apart, not just the distance between clusters increasing slowly over time, but space itself is expanding. The very fabric of reality is stretching. Every moment, every second, every breath you take, the universe grows a little larger. And it doesn't need a center to do it. It expands everywhere, equally, all at once. The distance between galaxies isn't increasing because they're moving through space, but because the space between them is becoming more of itself. Imagine dots on the surface of a balloon. As the balloon inflates, the dots grow farther apart, not because they're crawling away, but because the surface between them is expanding. Now imagine that, but in 3 dimensions. No edge, no outside, just more distance unfolding between everything. This is what the universe has been doing since the Big Bang. But here's the part that's even stranger. The expansion isn't slowing down. It's speeding up. This wasn't always expected. For decades, scientists assumed that the pull of gravity exerted by all the matter in the universe would gradually slow the expansion, maybe even reverse it one day. The cosmos would stretch, then contract, folding back in on itself. But in the late 1990 seconds, observations of distant supernovae revealed something else. The galaxies weren't just moving away, they were accelerating. Something unseen, something not yet understood, was pushing everything apart faster and faster over time. We called it dark energy, a name for an unknown force, a placeholder for a mystery. Whatever it is, it now dominates the behavior of the cosmos. It isn't just that galaxies are moving away from us, it's that in the far reaches of space, they're being carried so quickly that their light may never reach us again. The faster they recede, the more stretched their light becomes. Eventually, the wavelengths get so long that the light becomes undetectable, fainter than faint, gone. That means, one day, most of the universe will disappear from view. Not because it has gone anywhere, but because it has receded beyond the edge of the observable. That edge isn't a wall or a boundary. It's a limit set by the speed of light and the age of the universe. We can only see as far as light has had time to travel. And as space expands faster and faster, more and more galaxies will cross that limit, vanishing from our skies forever. The universe grows, and yet our visible portion of it shrinks. We live in a bubble of observability. It's vast, 93 billion light-years across, but it is not infinite, and it's slowly becoming lonelier. Galaxies we can see today will one day be gone. Not gone in themselves, but gone to us. Their light will never reach our telescopes again. It's as if they're slipping beneath the surface of a cosmic horizon, leaving only silence in their wake. Eventually, only the local group, the Milky Way, Andromeda, and a few small companions will remain visible. Everything else will be too far, too fast, too distant to detect. Future astronomers, billions of years from now, may look into the sky and see only darkness beyond their own galactic neighborhood. No trace of a wider cosmos, no hint of expansion, no evidence of the Big Bang. The universe will look static again, but it won't be. It will still be growing. It's just that the growing part will be unreachable, carried away on a wave we cannot follow, stretched across a sea we cannot cross. The universe will continue to expand, silently, endlessly, into a future without limit. And we'll be here, floating in a pocket of memory, watching the stars fade. In this way, time is a kind of eraser. It reveals, then it conceals. It gives us a glimpse of the grand design, the threads of galaxies, the deep clusters, the far-off quasars, and then gradually takes them back, slipping them out of reach. The cosmos shows itself for a moment, then retreats. But for now, we are living in the brief window when the universe is still visible. We can still measure its growth. still trace the ripples of the past, still listen to the microwave echo of creation, still glimpse galaxies so distant that their light began its journey before Earth even existed. We are here at the moment when the universe speaks its story loud enough for us to hear, a chapter where distance means time and space itself is fluid. A moment when the cosmos reveals its movement not just of stars or galaxies, but of itself, unfolding in all directions at once. We think of expansion as an action, but here it's a background. It's the quiet setting of everything. And like all great settings, it doesn't scream. It just is, always moving, always becoming more. We are not standing still. We are riding on a growing wave of space. And though we may never touch the galaxies slipping away, we carry their light. We hold their memory in photons, in patterns, in quiet understanding. We are part of a universe that expands not just through space, but through time, and through the minds able to wonder at it. If you were to leave Earth tonight, not in a metaphor, but truly step into a spacecraft and drift away from the planet, past the moon, past Mars, past the far orbit of Neptune, you'd be forgiven for thinking you were entering a place filled with stars. The night sky suggests that, a dome of glittering light, points strewn generously across a velvet black. It feels crowded, like the universe is full, but space is not full. Space is almost entirely nothing. The nearest star beyond our sun is Proxima Centauri. It's close, astronomically speaking, just 4.2 light-years away. But light travels at 300,000 kilometers per second, and it still takes more than 4 years for that light to reach us. That means even the closest neighbor in the vast city of stars is staggeringly far, roughly 40 trillion kilometers. If you tried to drive there at highway speed, say 100 kilometers per hour, you'd arrive in about 50 million years, and the road would be dark the entire way. The human mind isn't built to grasp emptiness like this. Our lives are built in scales we can hold. Rooms, buildings, roads, even airplanes and oceans feel vast but tangible. We can measure them. We can traverse them. But between the stars, there's so much nothing. It's almost like negative space. You could fit the entire solar system, a region that already stretches billions of kilometers over 1,000 times, in the gulf between us and the next star. And in that gulf, there is silence. It's not the silence of a quiet room or a still night, but something deeper, a silence that has never been broken. No wind, no air, no sound, just particles too sparse to notice and radiation too faint to feel. Light crosses these distances as if wandering through an empty cathedral, uninterrupted and unseen. Even the areas that feel busy by cosmic standards are mostly void. Within galaxies, stars seem to cluster close together, creating the illusion of density. But even in the densest regions of a spiral arm, the stars are so far apart that if our sun were the size of a basketball, the nearest star would still be hundreds of kilometers away. Galaxies are not glowing clouds of matter. They're islands of rare flickers separated by oceans of dark. And yet, somehow, this emptiness holds everything together. Gravity, weak as it is, stretches across this vacuum, pulling stars into orbits, shaping galaxies, sculpting the evolution of the cosmos. Photons, birthed in the hearts of stars, spend thousands of years escaping their source, and then tens of thousands more just crossing the gulfs within a single galaxy. Some have been traveling for billions of years, only to arrive in our skies as pinpricks of ancient fire. The space between isn't just far, it's cold, near absolute zero in places, just a few degrees above the coldest temperature physics allows. Atoms drift alone for years before encountering another. A single cubic meter of interstellar space might contain just a few stray hydrogen atoms. The space between galaxies is even more barren. Intergalactic space is so empty, it's hard to describe it as a vacuum, because even vacuums on Earth, sealed, pumped, and controlled, contain more matter. And yet this emptiness is not meaningless. It's the canvas on which everything else is drawn. Without this vast quiet between stars and systems, light wouldn't travel, galaxies wouldn't form, gravity wouldn't sculpt structures with such elegance. The darkness gives shape to the light. The absence defines the presence. It is precisely because of the void that the stars seem so brilliant when we look up from Earth. Even the solar system, our local neighborhood, is mostly space. The planets may seem tightly packed in models and diagrams, but those images lie by necessity. If you made a model where Earth and the Sun were a meter apart, Neptune would be nearly 30 meters away, and the nearest star would be more than 270 kilometers down the road. And between all those points, nothing. The Voyager spacecraft, launched in 1977, has been traveling for nearly half a century. It's now more than 20 billion kilometers from Earth, further than any human object has ever gone. And yet it hasn't reached another star. It hasn't passed another planet in decades. It's still in our cosmic backyard, still wandering through a darkness that doesn't end. And that darkness doesn't just surround us, it waits. Because space isn't just about what's out there, it's about how we live inside it. Our lives are bound to one fragile world, circling one average star in a sea of invisible distances. We build our homes, launch our satellites, send out radio signals, all inside a thin shell of atmosphere pressed against an ocean of vacuum. When astronauts go into orbit, they don't go very far, just a few hundred kilometers up, barely above the skin of Earth. But even there, they can see it, that black sky, the unforgiving vastness just beyond the curve of the planet. They know what we forget. That space isn't far away. It's right there, waiting outside the window. And in that awareness is something humbling. We like to imagine ourselves at the center, but in truth, we live in a margin. A small blue island surrounded by billions of kilometers of nothing. The universe is mostly not us, not matter, not light, not life, just space. And somehow, in all that emptiness, we found a place to call home. At the edge of the visible universe, there are lights so bright they outshine entire galaxies, not stars, not clusters, but something stranger. Beacons so distant and powerful that their glow has crossed billions of light years just to whisper to our telescopes. These are quasars, and their existence bends what we think we know about how light works, how galaxies live, and what it means to be powerful in a place like this. A single quasar can shine with the intensity of 1 trillion suns. That's not poetry, that's measurement. They radiate more light than every star in their home galaxy combined. Not for a moment, but for millions of years. And unlike a star, which shines from fusion deep within its heart, a quasar burns through destruction. At their core lies a black hole, a supermassive one. But instead of hiding in darkness, these black holes roar with light. Not from within. Nothing escapes from inside, but from the chaos just outside the edge. Matter spirals inward, caught in the pull of gravity so intense it can't resist. As it falls, it heats. Friction, pressure, magnetism, all of it ignites a storm of energy. Gas and dust swirl at near light speed, glowing with heat, compressed and accelerated until they blast out radiation across the spectrum, visible light, X-rays, ultraviolet, and more. This storm, this blazing maelstrom of doomed matter, becomes the quasar's voice, and it can be heard across the universe. What's even stranger is how focused they can be. Some quasars shoot jets, narrow beams of particles and radiation that erupt from the poles of the black hole's magnetic field. These jets don't just radiate, they pierce. They cut through space like cosmic lighthouses, and if one happens to aim toward us, the brightness we see multiplies dramatically. It's not because it's closer, but because the beam is concentrated, like the focused glow of a flashlight in a dark room, and that beam can travel for billions of years before reaching our eyes, which means when we observe a quasar, we're not looking at what it is, we're looking at what it was. Many of the brightest quasars we know today existed when the universe was still young, just a fraction of its current age. They are fossils of light, still burning in our sky from a time when galaxies were still forming, when stars were just beginning to arrange themselves into patterns. They tell us how galaxies grow, because here's something else. Quasars live at the centers of galaxies. That means every quasar is a signal of something bigger. The galaxy wrapped around it might be invisible to us, too faint to see, too far to resolve, but it's there, a swarm of stars orbiting the monster at its heart. In fact, astronomers believe that nearly every massive galaxy, including our own, has a supermassive black hole at its center. The Milky Way's central black hole, Sagittarius A*, is quiet now. It doesn't feed, at least not much. But if it were to awaken, if a cloud of gas wandered too close and began to spiral in, it could flare into a quasar of its own. For a time, our galaxy would shine like a beacon across the cosmos. This idea that galaxies grow around black holes instead of the other way around changes how we see the sky. It means that brightness isn't just about stars, it's about hunger. It's about gravity, dragging matter into collapse, and that collapse turning into radiance. Light made not by life or warmth, but by annihilation. And in that annihilation, the structure of the universe takes shape. There are quasars whose light left them before Earth was even a planet, before the sun existed, before the atoms in your body were forged. The signal has been traveling all that time, undisturbed, carrying with it the story of a place that may no longer exist. Because a quasar is a phase, a brilliant, violent chapter in a galaxy's history. They don't last forever. Eventually, the black hole runs out of nearby material to consume. The disk cools, the light fades, and all that's left is the black hole, still there, still heavy, but quiet. Like a bonfire that burned through the night and left only ashes behind. But the light keeps going. Even after the quasar goes dark, the photons it released keep crossing space, undisturbed, their path shaped only by gravity and time. They carry a message across a universe that's expanding beneath them. They stretch as they go, their wavelength pulled by the growing fabric of space, until they arrive thinner, older, but still glowing, still enough for us to detect, still loud enough to be heard. And so, we point our telescopes to the deep. We find them dots of impossible brightness, flaring in places where nothing should shine. We map them, we count them. We use them as markers to trace the edges of the observable. And every time we find one farther than the last, we're not just seeing light, we're seeing time. A moment when matter lost itself to gravity and became something louder than stars. Quasars remind us that the universe is not always gentle. It isn't always cold and slow. Sometimes it flares. Sometimes it screams. And in that scream is a kind of beauty, because even destruction, when seen from this distance, can look like a candle in the void. Long before there were stars, before galaxies spun themselves into spirals and light formed patterns in the sky, there was a moment hot, dense, and full of motion. The entire universe was compressed into a state of unimaginable heat and pressure, a churning ocean of particles so tightly packed that light couldn't travel without being swallowed. Photons, particles of light, bounced endlessly from one particle to another, unable to escape, unable to stretch their wings across space. And then something changed. Roughly 380,000 years after the Big Bang, the universe had expanded and cooled just enough for atoms to form. Electrons settled into orbit around protons. The fog of charged particles cleared. For the first time, light was free. Those photons, once trapped in the storm, began their journey outward. Not for minutes, or years, or even centuries, but for billions of years. They've been traveling ever since, uninterrupted and unhindered, slipping through space as it stretches beneath them. That ancient light is still around us, still falling into our eyes, still whispering in microwave frequencies too faint for us to hear unaided. It's called the cosmic microwave background, or CMB, a soft echo from a time when there were no planets, no stars, not even the building blocks of life. Just expansion, just silence, just the slow cooling of everything. This light isn't visible in the way starlight is. It's been stretched wavelength, pulled like taffy by the expansion of space itself. What began as searing, short wavelength radiation has cooled with the universe, diluted by distance, until it rests now in the microwave band. A soft hum of temperature just 2.7 degrees above absolute zero, not because the light itself cooled, but because space everything grew between it and us. You can detect it with a radio dish. You can even hear traces of it on an old television tuned to static. That hiss between channels? A few percent of that noise is the CMB, not noise from Earth or a satellite or a storm in the ionosphere, but from the very birth of time. And yet, this light is astonishingly smooth. It glows with almost perfect uniformity, the same in every direction to 1 part in 100,000. But those tiny fluctuations, those minuscule ripples, are everything, because inside those ripples were the seeds of structure, slightly denser pockets of gas that, over billions of years, would become stars, galaxies, and clusters. Every planet, every star you've ever seen, every atom in your body, started as a bump in the background hum. The CMB is not just a relic, it's a map, a photograph of the baby universe, still wrapped in its first light. And when scientists point telescopes like the Planck Observatory or the Wilkinson microwave anisotropy probe toward the heavens, they capture that map in exquisite detail. They chart its cold and warm patches, its fingerprints from inflation, its subtle asymmetries, and in doing so, they learn not just about the past, but about everything since, because the universe hasn't stood still. As those photons raced outward, the universe expanded beneath them. Space itself stretched, which means light stretched too. This isn't like watching a beam of light move through air or glass. It's more like watching the surface of a balloon stretch after the ink has dried. The wavelength grows longer, the energy shifts, and what was once brilliant becomes background. That's the strange thing about the CMB. It's not a glow from behind the stars, it is the farthest thing we can ever see. Beyond it lies the opaque era, the cosmic wall of fog before light could move. No telescope can peer through it. No signal can reach us from earlier. It is, in a very real sense, the edge of visibility, the edge of time. But it is not the end. Because what it tells us isn't just that the universe had a beginning, it tells us how that beginning unfolded. It reveals the shape of space, the rate of expansion, the fingerprints of dark matter and dark energy. It's the baseline hum against which all other cosmic music plays, and it's still playing. Every second, those photons continue their journey. Some pass us by, some fall into telescopes, some drift for eons yet to come. Light, after all, is patient. It doesn't need a destination. It simply travels, carrying its story with it until something stops it. And we, for a brief moment, are fortunate enough to listen. We are not the center of the universe, but we are surrounded by the echoes of its birth. They are not loud, they do not dazzle, but they are vast and old and everywhere. And all they ask is that we notice. Right now, as you listen, trillions of particles are slipping through your body. They move like whispers, silent and invisible, passing through skin, through organs, through bone. They come from the heart of the sun, from the collapse of ancient stars, from cosmic collisions so distant that their light hasn't reached us yet. They come from everywhere. They always have. These particles are called neutrinos, and they are among the strangest things in the universe. They have almost no mass, they don't carry a charge, and they barely interact with anything. In the vast world of physics, they are ghosts, not because they are supernatural, but because they are almost entirely untouchable, 100 trillion neutrinos will pass through your body in the time it takes you to blink, and you'll never feel a single one. They travel at nearly the speed of light. They are not stopped by water or metal or mountains. In fact, to reliably block a stream of neutrinos, you'd need a wall of solid lead several light years thick. Which means that when a neutrino is born, it doesn't care what's in front of it. It simply goes. And yet, for all their indifference, they are storytellers. Every second, the sun produces an enormous storm of neutrinos. They pour out from the nuclear fusion deep inside its core, created when hydrogen atoms fuse into helium, releasing light and heat and these phantom particles. Those solar neutrinos reach Earth in just over 8 minutes, arriving in such numbers that each square centimeter of your skin receives millions every instant. They sail through you as if you aren't there, as if nothing is. But solar neutrinos are just the beginning. Some neutrinos are older than Earth itself. Formed in the Big Bang, they have been traveling for nearly 14 billion years. Others were forged in supernovae, the final, furious moments of massive stars exploding outward. In the instant that a star dies, the collapse of its core squeezes matter so tightly that the laws of physics begin to bend. In that chaos, a flood of neutrinos is unleashed, carrying away most of the energy of the event. For every flash of visible light from a supernova, there is an unseen torrent of neutrinos, racing away in every direction, leaving behind the ruins of a star and the birth of something new. Because of this, neutrinos are messengers. They arrive long before the light. In fact, when a nearby star goes supernova, scientists may first detect it not with a telescope, but with a neutrino detector, a vast underground chamber filled with pure water or ice, shielded from cosmic rays and background noise, waiting in near silence for the faintest trace of a neutrino interaction. Those detectors are massive, but they're also patient. They know neutrinos rarely speak. They can pass through Earth without touching a single atom. But now and then, a rare one will collide just right. It will graze a proton or brush against a neutron, and for the briefest of moments, leave behind a mark, a spark of light, a ripple in a sensor, a whisper caught in the dark. From these rare interactions, we learn. We learn about the inside of the sun, places we'll never visit, deeper than light can reach. We learn about the death of stars, the formation of neutron stars and black holes. We learn about distant galaxies, about cosmic rays, about the fabric of the universe itself, all through particles that never stop, never rest, and almost never notice us back. They don't slow down, they don't decay. Once created, a neutrino simply moves forward, across planets, through stars, between galaxies. It is possible that a single neutrino created in the Big Bang is still flying through space today, unchanged, having crossed the entire observable universe countless times over without touching a thing. They remind us that the universe is not just vast, it's permeable, that there are things moving through us all the time, unnoticed, unmeasured, and unstoppable. We imagine space as something far away, but in truth, it's inside of us. Not metaphorically, literally. With every second, particles from the sun, from ancient stars, from cosmic explosions, pass through the atoms of your body without ever pausing. The void is not empty. It's full of motion. And neutrinos are its quiet runners. They don't sparkle like starlight. They don't pulse like quasars. But they are everywhere, constant, tireless, and strangely elegant in their simplicity. They are the ultimate minimalists, barely there, but enough. Enough to carry a signal, enough to keep moving, enough to teach us that even the quietest thing can hold the oldest truth. You are not separate from the universe. You are stitched into its field, part of its current, threaded through by particles that began their journey long before you were born. Particles that don't see your outline, your surface, your weight, only space. They pass through the mountain you stand on, through the planet itself, through you, and they never stop. There are stars in the sky that have watched everything unfold. Before the Milky Way spun itself into a spiral, before our sun was born, before Earth had form or name, they were already burning. Small, dim, long-lived, but ancient beyond imagination. When you look at them, you're not seeing just a distant light. You're seeing time, distilled into flame. These stars are the survivors of the first generation. Not the very first stars, those were giants, wild and short-lived, devouring their fuel in a flash and disappearing into black holes before the universe had time to breathe. No, these are second-generation stars, born from the remnants of that first chaos, formed from clouds, seeded with the ashes of the original fire. These stars hold clues in their chemistry, little markers of what came before, a fingerprint of a time when the universe was still finding its rhythm. They drift quietly, tucked into the halo of our galaxy, orbiting in long, looping paths that can take billions of years to complete. They don't belong to the bustling, bright disk of the Milky Way. They wander its outskirts, like elders watching from the edge of the room. Their names are cataloged in numbers and designations: HD 140283, SMSS J313 6708. But what they represent is older than any name we could give them. The light they shine is not special to the eye. It's not especially bright or colorful. But when that light is broken down into its spectrum, a story emerges. Scientists read these spectra like archaeologists reading stone tablets. Gaps in the light reveal elements missing from the stars. No iron, no carbon, no heavy metals. These are stars that formed before those ingredients existed in large amounts. Stars born when the universe was still chemically simple, before the factories of supernovae had made the periodic table full. Their existence means that, somehow, through the turbulence of early cosmic formation, a few stars managed to last. Stars that shouldn't still be here and yet are, burning slowly, softly, refusing to go out. They are clocks without hands, calendars without numbers, but they mark time all the same, a record not in ink, but in presence. And the light from them is a message, traveling for billions of years through expanding space, a ribbon unspooling from the past. That light has crossed distances we can't fully grasp, not just across the galaxy, but across time itself. In the space between then and now, everything happened. Galaxies collided, planets formed, life crawled onto land, cities rose and fell, empires blinked into being and faded. Every moment of your life, every breath you've ever taken, unfolded while that starlight moved toward you. There's something quieting about that. To know that, right now, a photon of light from a 1-3 billion-year-old star might be entering your eye, striking your retina, and becoming part of your awareness. Light that left its source long before the Earth was even a thought. Light that has traveled unbroken across the fabric of the cosmos, unaffected by war or weather, passing stars and voids and dust, until it finally reached you. Not metaphorically, physically. That light is real, and it's touching you. In this way, the universe sends us letters, not in language, not in sound, but in light, in age, in the chemical signatures of stars so old they predate the shape of the galaxy itself. They tell us that something existed before structure, before systems, before the swirling arms of the Milky Way found their spin, and it's still here, still glowing, still waiting to be seen. We often think of time as something we move through, as if we're walking down a road, leaving moments behind us, watching new ones approach. But in truth, time is something layered, something we're surrounded by. Every star is a different time. Every point of light in the night sky comes from a different distance, a different age. You're not looking at one present, you're looking into a mosaic of millions of pasts, all stitched together in silence. And some of those pasts are nearly the beginning. The oldest known stars carry whispers of the Big Bang in their makeup. Not just their age, but their composition. They tell us what was possible when the universe was new, what could form, how matter cooled, how the first structures coalesced. They help us rebuild the sequence of creation, not through stories or mythology, but through chemistry, through light, through silence. It's humbling to think that we are latecomers, that everything we've ever known, the oceans and animals and inventions and histories, all came after these faint, quiet suns. They are not our ancestors in a biological sense, but in a cosmic sense, they absolutely are. They watched the early universe stabilize. They held steady as the first galaxies lit up. They remained constant through eons of collapse and creation. And they're still here, still burning, still sending us messages in every photon, far beyond our solar system. Orbiting a star too faint to see with your eyes, there's a planet that may shimmer with something we once considered rare. Not water, not air, but diamond. Its name is 55 Cancri E, and it doesn't behave like anything familiar. It's a world so close to its star that a single orbit takes just 18 hours. On its surface, temperatures soar past 4,000 degrees Fahrenheit, hot enough to melt metal, warp molecules, and split atoms apart. There's no night there, no cool side, no seasons, just heat, relentless and unchanging. But beneath that fiery exterior, buried within its carbon-rich mass, is the possibility of something dazzling, a planet where pressures and temperatures are so extreme that carbon abundant and rearranged may have crystallized into something dense, clear, and brilliant. A planet where diamond isn't a rarity locked deep inside the crust, but a foundational element of the world itself. If you could stand on 55 Cancri E, you wouldn't see glinting gemstones underfoot. You'd see a surface scorched into magma, the sparkle buried under layers of molten carbon and alien minerals. But it would still be there, silent, compressed, enduring. It defies our instincts, this idea, because on Earth, diamonds are symbols of beauty, of rarity, of permanence. We think of them as impossibly precious. But in the cosmos, value isn't defined by desire. It's defined by conditions. And when carbon is pressed by gravity and scorched by heat, it doesn't ask what we want. It simply becomes what it must be. In some corners of the galaxy, diamond may be as common as granite, and 55 Cancri isn't even the strangest. There are planets where the rain cuts sideways in glass shard sheets, driven by winds that move 7 times the speed of sound, where the skies burn with plasma arcs, and clouds of vaporized rock swirl above oceans of lava, where shadows shift color, not because the sun is setting, but because the sky itself is made of vaporized metals, sodium, potassium, vanadium, shimmering like a molten mirror. There are planets where 2 suns rise and 2 shadows stretch across the ground, twisting and merging in ways no earth-born eye could ever fully predict. Some of these worlds are giants, hundreds of times the mass of Earth, with gravitational pulls that would crush bone and flatten lungs in seconds. Others are small but dense, like iron marbles in the dark, so heavy and compact they barely allow space for an atmosphere at all. There are rogue planets drifting between stars with no sun of their own, frozen, lonely, and lightless, yet massive enough to hold moons and magnetic fields. Worlds adrift in the dark, waiting, not for discovery, but simply to continue. And still, others burn cold. Neptune-sized planets with icy cores and methane skies, where temperatures hover so low that nitrogen rains down like snow. Or tidally locked planets, where one side is blistering desert and the other an eternal night. 2 climates divided not by latitude, but by orbit itself. On those worlds, wind never stops. It howls from one hemisphere to the other in a jet stream of desperation, endlessly trying to equalize a balance that cannot exist. Scale, in the universe, is not just about size, it's about strangeness, about the range of what's possible when gravity, temperature, pressure, and time are allowed to experiment without the boundaries of human expectation. The universe does not follow the rules of habit. It explores every corner of physics, every edge of chemistry, every unlikely outcome, and it repeats them not once, but endlessly. If you can imagine it, the universe has already built something stranger. If you can't imagine it, it has likely built something stranger still. We've only just begun to glimpse them. Most exoplanets are discovered not by sight, but by shadow. A brief dimming of a star's light as a planet passes in front of it. From that, astronomers calculate size, mass, orbital distance. From the wobble of a star's gravity, they infer weight. From the way light filters through a planet's atmosphere during transit, they estimate gas composition. It's all math, inference, a dance of variables, deductions, and models. But what we find, over and over again, is not repetition. It's wild variance. Planets where it rains molten iron, planets with atmospheres thick in carbon monoxide and titanium oxide, planets with days that last years, planets with no surface at all, just clouds, storms, and swirling gas that deepens infinitely into pressure and heat. These places do not obey the scripts of habitability, but they are real, and they are out there in numbers beyond comprehension. For every star, there are likely multiple planets, and for every planet, an entirely new set of rules. And somewhere in that infinite scatter, you might find a planet with a core like a gemstone, spinning silently beneath a heat-wave sun. Not because the universe meant to make it beautiful, but because beauty is sometimes what happens when nature forgets to be ordinary. 55 Cancri E may never be visited. Its surface may remain unmeasured, its diamond heart unconfirmed. But its presence teaches us something more important than certainty. It teaches us to expect difference, to expect wildness, to expect that the universe is not just bigger than we think, but more imaginative. We look up and see stars, but hidden among those lights are billions of worlds stranger than fiction, not just bigger, wilder, older, colder, hotter, and sometimes, in the quiet gravity of just the right place, impossibly hard, endlessly shining. In 2022, a single image changed the way we understand distance. Not in miles, not in kilometers, not even in light years, but in time. Captured by the James Webb Space Telescope, it was a photograph unlike any other, a deep field image, small enough to cover a grain of sand held at arm's length, yet vast enough to contain thousands of galaxies, spirals, smudges, and specks, each one a city of stars, each one a relic of a different age. Some were young, still forming their first suns. Others were ancient, dimmed, and stretched by the expansion of space. And some, many no longer exist at all. Because when you look that far, you're not looking across space, you're looking backward. Every beam of light has a starting point, and when it leaves a galaxy 13.5 billion light-years away, it begins a journey so long that entire civilizations could rise and fall 1,000 times before it ever arrives. Light, the fastest thing we know, still takes time to travel, and in a universe this big, that time becomes an archive. A telescope doesn't just magnify, it reads the library of existence. The farther it sees, the older the chapter. The Webb telescope, with its gold-coated mirrors and infrared eyes, is a time machine, quiet, precise, patient. Point it at the darkness and wait long enough, and the past will speak. That deep field wasn't a wide view. It wasn't designed to impress with scope. It was designed to reveal density, how much can fit into a single corner of the sky. And the answer, as always, was more than we imagined. Hundreds of galaxies, thousands, layered atop one another, distant beyond reason, glowing not because they are bright now, but because they were once bright enough for light to survive the stretch. You are not seeing them as they are. You are seeing them as they were. Some of those galaxies, the oldest ones, formed only a few 100 million years after the Big Bang. At that time, the universe was still dark, still filled with the last wisps of opaque gas left over from the cosmic dawn. These were among the first structures to gather mass and ignite stars, primitive, small, irregular, and yet bursting with energy. Their light had to travel through epochs of transformation, through the apost, formation of larger galaxies, the dance of gravity, the expansion of space itself just to reach us. When that light left, Earth did not exist. The sun did not exist. Nothing resembling our solar system had yet formed, and yet that light found us. Captured in a detector, stored in data, rendered into color. What you're seeing isn't light in the way your eyes detect it. It's infrared heat stretched across distance, invisible to humans but not to Webb's gaze. Scientists translate that data into visible tones, assigning colors that represent energy, wavelength, and structure. It's not a false image, it's a different language, one we've only just begun to understand. You can look at that image and feel small, and you should. Each dot of light is a galaxy. Each galaxy, billions of stars. Each star, potentially planets. Each planet, perhaps life. But it's not just about quantity, it's about time. Because the image isn't just full of things, it's full of befores. Befores stacked on befores, each layer a thinner echo of reality. That's the great paradox of astronomy. The deeper you see, the longer ago you're seeing it. The edge of the observable universe isn't a wall. It's a moment, a frontier of memory so distant it begins to blur with creation itself. What's strange is this: some of the light in that image is older than what we thought should be possible. Galaxies that formed earlier than our models predicted, stars that assembled faster, structures more mature than they should have been, given the time. The universe, it turns out, might be better at building than we expected. Or maybe our understanding is still young. Maybe, like the light we collect, our ideas are always a little behind. The deep field isn't just an image, it's a challenge. Because every new observation stretches our assumptions. Every faint smudge calls for recalibration. What is a galaxy supposed to look like at 13.5 billion years ago? What if there's no supposed to at all? What if the cosmos isn't just bigger, but more adaptable, more improvisational than we gave it credit for? And still, it keeps going. The Webb telescope will continue to look, to wait, to stare into silence. It will target even deeper fields, longer exposures, narrower filters. It will pull secrets from shadows. Dust clouds will become transparent. Cold stars will flare to life in its sensors. Collisions, outbursts, births, and deaths, all frozen in that thin slice of sky. Light that has traveled through more time than any human mind can truly comprehend, finally arriving to be caught and recorded. That's what's so humbling. Because when we look up, we think we're seeing now. But we're always seeing then. The night sky is not a dome. It's a cathedral of memory, a curved mosaic of light running late. And that deep field image? It's the closest thing we've ever had to touching the beginning. Not by traveling there, but by receiving what left it long ago. In every pixel of that photograph, there's a story, one you'll never finish. One the universe is still telling. One it's been whispering without interruption, since before we had ears to hear. Somewhere in the quiet of the outer solar system, in the deep cold where sunlight arrives more as suggestion than warmth, moons are doing strange things. They spin in silence around distant planets, circling with grace, rebellion, or something in between. Some move obediently, rising and setting like clockwork shadows. Others break the rules. They orbit backwards, or at steep, cockeyed angles that make no sense at first glance. They don't need to. Space doesn't answer to our instincts. It writes its own logic. Jupiter alone has nearly 100 moons. Most of them small, captured asteroids or icy fragments, ancient relics caught in its enormous gravitational web. But 4 stand out: Io, Europa, Ganymede and Callisto, the Galilean moons, each one a world, not just a rock. Ganymede, the largest of them, is bigger than Mercury. It has its own magnetic field, a rare trait among moons. Beneath its frozen crust may lie a saltwater ocean, vast, deep, sealed off by miles of ice. A world within a world, where tides rise and fall in total darkness, stirred by the slow squeeze of gravity. Europa is smaller but even more intriguing. Its surface is etched with lines and cracks like the veins of a leaf, scars from the push and pull of Jupiter's immense gravity. Scientists believe a global ocean lies beneath, kept liquid not by sunlight, but by friction, gravitational kneading, warming the interior, like hands shaping dough. It's one of the best places we know to search for life. Not alien civilizations, but microbes. Something simple, something ancient, something surviving in silence for eons. Io, by contrast, is anything but silent. It's the most volcanically active body in the solar system. Geysers of molten sulfur erupt from its surface, driven by the same gravitational stresses that stir Europa's seas. Instead of oceans, Io has lakes of lava, and its terrain shifts constantly as new eruptions reshape the land. It's a moon that screams through geology, forever reshaping itself in a tantrum of heat and motion. Then there's Callisto, darker, quieter, battered by craters and time. Its surface tells a different story, one of endurance rather than transformation. Yet even here, some models suggest an underground ocean might still exist, insulated beneath the crust. It's a pattern that repeats across the outer solar system. The farther you go, the more moons you find with hidden seas. Saturn, ringed and regal, has its own court of strange companions. Enceladus is small, but it defies expectations. From its south pole, plumes of water vapor and ice erupt into space, like geysers from a frozen Yellowstone. We've flown through those plumes with spacecraft and tasted their chemistry. They contain water, organic molecules, and hints of energy, three of the fundamental ingredients for life. The ocean beneath Enceladus's crust is not hypothetical. It vents into space. We've seen it. We've flown through its breath. Titan is Saturn's largest moon, and it doesn't just have oceans, it has weather. Lakes and rivers of methane flow across its surface. Rain falls from hydrocarbon clouds, carving valleys and shaping shores. It has a thick atmosphere, orange and hazy, hiding a solid surface below. To land on Titan is to walk through alien humidity, in a world where water is frozen rock and rivers run with liquid gas. And further out still, around Neptune, lurks Triton. This moon is a rebel. It orbits backward retrograde, moving against the planet's spin. It may have once been a dwarf planet, captured by Neptune's gravity long ago. Its surface is pocked with geysers that spout nitrogen into the vacuum. It's bitterly cold, colder than almost anywhere else in the solar system. But still, it moves. Still, it breathes in a way, leaking heat from the inside out. These moons aren't side characters. They're entire chapters. Each one tells a different story about what it means to be a world. We used to think of moons as passive, lesser bodies, circling planets. But over time, we've learned that many are more geologically active, more complex, and in some cases, more promising for life than the planets they orbit. Their orbits defy neat categories. Some are nearly circular, gliding smoothly in the plane of their planet's equator. Others are wildly tilted, elongated, irregular. Some were born where they are. Others were stolen from elsewhere. Moons captured during chaotic gravitational dances, trapped into strange paths that don't settle, only persist. And the deeper you look, the more of them there are. It turns out that being a moon is less about size and more about circumstance. Pluto has 5 moons, despite being demoted from planethood. One of them, Charon, is so large, relative to Pluto, that the two actually orbit a point in space between them, like dancers holding hands around an invisible center. It's not a planet and its moon, but a binary system, a duet floating at the edge of sunlight. Even our own moon, so familiar and constant, is peculiar. It stabilizes Earth's tilt, slows our rotation, and gives us tides. It was likely born from a colossal impact, a splintered chunk of Earth flung into orbit and then molded by gravity. Without it, life here might have taken a very different path. Moons challenge our categories. They reveal how much variety can emerge when the same basic rules, gravity, heat, motion, are played at different volumes. Their oceans are hidden. Their skies are alien. Their orbits bend the expectations we carry from Earth. In the vast clockwork of the solar system, they are the gears that don't always tick in rhythm. And yet, they move. They echo. They whisper of stories written in heat, ice, and ancient collisions. They are reminders that even among the familiar planets, there are stranger companions quietly orbiting, holding secrets no planet ever dared to keep. In our skies, Saturn's rings feel like the crown jewel of the solar system, thin and luminous, spreading wide and glinting like ice dust filigree. For centuries, they were a mystery, then a marvel, and eventually a symbol of how strange and elegant the universe could be. But Saturn, as beautiful as it is, might just be a preview, a modest example, because out beyond the reach of any telescope we've built with earthbound hands, we're starting to glimpse something even stranger: rings that make Saturn's look like a bracelet next to a planet-sized halo. One of the first hints came from a star. Not a planet, not a ring, but a flicker, a rhythmic dip in the brightness of light, measured by patient instruments. The kind of pattern that suggests something is passing in front, blocking the starlight in strange and uneven ways. It wasn't a clean planet transit, the kind that produces a crisp shadow and a neat curve in the data. This one was messy, irregular, as though the thing doing the blocking wasn't just one solid body, but something wider, more intricate, more diffused. That something was J1407b, an exoplanet, massive and unseen directly, inferred by its gravitational fingerprint and the shadows it casts. And what it might wear around its waist isn't just a ring system, it's a planetary halo so vast it could stretch over 120 million kilometers across. That's nearly 200 times wider than Saturn's rings, a structure so immense that, if it were placed in our solar system, it would swallow Mercury, Venus, Earth, and Mars, all while still reaching out into the orbit of Jupiter. But unlike Saturn's icy ribbons, which measure just tens of meters thick and are composed of snowball fragments and dust, the rings of J1407b could be young, raw, and chaotic. They might not be stable. They might be in the process of forming moons, letting gravity knead the scattered debris into orbiting companions. We could be witnessing, from light years away, a planetary system in the act of sculpting itself. It's strange to think of a ring as something being born. We tend to see rings as decorations, the finishing touches on planets long settled into shape. But rings, like stars, have lifespans. They come from somewhere. They can fade, collapse, or even coalesce into new bodies. Some rings are remnants of ancient collisions, moons shattered by gravity or impact, ground into rubble and stretched into arcs. Others may be the slow erosion of comets or the byproducts of volcanic activity from nearby moons, like the wispy E-ring of Saturn, which is fed by geysers on Enceladus. So, when we look at a ring system larger than the orbit of Mars, we're not just seeing beauty. We're seeing history in motion, an architectural echo of the planet's past and maybe its future. What makes the rings around J1407b even more astonishing is how we saw them. Not with images, not with direct visual proof, but with shadows, like watching candlelight pass behind lace and trying to reconstruct the shape of every thread. These kinds of measurements are delicate, prone to noise, and require enormous patience. and yet they whisper of things so vast and elegant that we can barely grasp them. J1407b is just the beginning. It's likely not alone. As our instruments become more precise and our eyes stretch farther into space, more of these ringed giants may reveal themselves. Planets with crowns so enormous they defy category, dwarfing the worlds they surround. Some may be failed stars, brown dwarfs with ring systems that shimmer with dust and heat. Others might be rogue, wandering planets not tied to any star, carrying their rings with them through the galaxy like wandering monarchs. We don't yet know what all these rings are made of. Ice, dust, rocky debris, gas, maybe something entirely unfamiliar. But we do know they hint at structure, and structure means story. It means interaction, gravity, movement, creation, and erosion. Rings are shaped by their environments, by nearby moons, by magnetic fields, by collisions and tides. They're not static. They are alive in a slow, gravitational way. And if that sounds poetic, it's because it is. We tend to think of space as emptiness, but rings reveal how much matter lingers, how much memory is suspended in orbit, endlessly turning. They are planetary fossils, part history, part anticipation. They tell us what happened. They suggest what's coming. Imagine standing on a moon beneath such a ring system. The sky wouldn't just be stars. It would be layered in bands, bright, glittering arcs stretching from one end of the horizon to the other. Daylight would shimmer as it passed through them. Nights would glow. Even here, on Earth, under the weight of our own blue atmosphere, it's hard to fathom what such a sky would feel like. Not just to see it, but to exist beneath something so massive and permanent and gentle all at once. These are the kinds of discoveries that remind us how early we still are in understanding the universe. For all our telescopes and satellites, we're just beginning to notice the subtleties. We've cataloged thousands of exoplanets, but almost none of their rings, and that's likely not because they don't exist. It's because we haven't looked closely enough yet. The universe has more shadows to cast, more patterns to whisper through starlight. Saturn taught us what rings could be, but other worlds are showing us what rings can become. And somewhere, light years away, there's a ring big enough to span the distance from here to the sun, stretching through space like a quiet echo of gravity, carving its shape into the darkness, waiting patiently for someone to notice. Some forces in the universe reveal themselves with color and spectacle. Light dances, gravity pulls, matter collides, and the results are dramatic rings and stars and supernovae that leave us breathless with their scale and fire. But there are other forces quieter, stranger ones that don't dazzle the eyes or ripple across space in sound. They hum, they tug, they thread through the void like phantom fingers, shaping everything while remaining almost entirely unseen. Magnetism, for all its power, moves like a ghost through the cosmos. Here on Earth, magnetism is modest and domestic. It holds compass needles steady, lets birds migrate by invisible maps, and hums inside your devices with orderly reliability. But this is the shallow end, a local ripple in a much deeper ocean, because magnetism in space is a different thing entirely. It bends light, it tears atoms apart, it carves boundaries in plasma, and guides entire galaxies as if by a hidden hand. At the center of this magnetic mythology are magnetars, born from the ashes of massive stars that collapsed under their own weight. A magnetar is a type of neutron star, already among the strangest objects in the universe. Imagine something heavier than our sun, compressed into a sphere the size of a city. Its matter so dense that a single teaspoon would weigh billions of tons. But a magnetar takes that physics-defying object and layers on an even more astonishing trait: an unimaginably powerful magnetic field. How powerful? Trillions of times stronger than Earth's, strong enough to distort the shapes of atoms, strong enough to affect electronic equipment from thousands of kilometers away. If you brought a magnetar to the distance of the moon, Its field would erase every credit card on Earth and destroy our entire telecommunications infrastructure. But it wouldn't need to come close. Magnetars don't travel. They spin sometimes hundreds of times per second, sending out bursts of radiation, flickering in X-rays, and occasionally flaring in powerful explosions that can be detected across galaxies. They are rare, maybe only a few dozen in the Milky Way, but their presence echoes outward, shaping the space around them like a silent scream held in tension. Magnetism doesn't just belong to collapsed stars, it lives in the empty spaces too, where emptiness isn't truly empty. Galactic magnetic fields extend for light years, swirling and stretching, subtle and ancient. They don't shine or burn, but they sculpt. They guide jets of plasma from black holes, channel cosmic rays, and slow down charged particles from interstellar winds. Entire galaxies can exist within soft magnetic cocoons, like bubbles blown from the core, wrapping their spirals in unseen lines of force. We don't see these fields directly, but we feel their influence. When we map the motion of gas, when we trace the alignment of dust particles, when we look at the patterns of polarization in starlight, we glimpse the invisible threads. They stretch like latticework across the cosmos, joining galaxies in tenuous filaments, draping clusters in subtle veils. These are the skeletons of the large-scale universe, magnetic scaffolding laid over dark matter and gravity, helping to organize the chaos. It's easy to overlook magnetism because it doesn't behave like light. It doesn't offer easy visuals. It's not a point of brightness or a colorful explosion. It's structure without spectacle. It's architecture that you only notice once you understand what it's holding up. But imagine if we could see magnetic fields the way we see sunlight. The galaxy would glow with lines, spirals wrapping around arms, jets radiating from cores, bubbles puffed out from stellar nurseries and supernova remnants. The night sky wouldn't be darkness filled with dots. It would be a tangled jungle of invisible highways, each one guiding particles, shaping starbirth, buffering collisions. You'd see the universe as a living machine, humming with currents that stretch farther than you can measure. And it's not just galaxies. Even planets have magnetic personalities. Jupiter's field is so large it extends beyond the orbit of some of its moons. Earth's field, meanwhile, protects us every second of every day from the solar wind, a constant stream of charged particles hurled at us from the sun. Without it, our atmosphere would be stripped away, and life might never have emerged at all. The auroras are one of the few places where magnetism puts on a show. When charged solar particles slam into Earth's upper atmosphere and get redirected by its magnetic field, they spark curtains of light in the sky, green and purple waves that ripple and dance. But even that is a hint, a quiet gesture. Most of what magnetism does happens in silence, in darkness, behind the curtain. Some scientists believe the universe's magnetic fields were born in the earliest moments after the Big Bang. Tiny imbalances in plasma flows, amplified over billions of years, could have stretched into the vast intergalactic fields we detect today. Others suggest they emerged later, seeded by galaxies and stars, growing outward like roots from a central tree. Either way, they are ancient, older than stars, older than planets, a part of the foundational energy that shaped everything we see. And just like gravity, they never stop. The more we look, the more we find magnetic fingerprints in places we didn't expect. In cosmic voids once thought to be completely empty, in faint filaments between clusters, in the swirling chaos around merging galaxies, they're not always strong. Often they're barely measurable, but they're there, like a memory etched into space itself. We are still only beginning to understand how deep this influence runs. Magnetism doesn't just respond to the universe, it helps write its story. From the formation of stars to the jets from quasars, from the shielding of planets to the dance of solar winds, these invisible forces whisper through every chapter. You don't need to see them to believe in them. They are the quiet architects, the hidden tension beneath the beauty, the lines you never see that hold the stars in place. They fall silently, constantly, like an invisible rain, not of water or dust or even light, but of ancient particles born in the most violent corners of the cosmos. These are the messengers from the edge cosmic rays, traveling across staggering distances, through the void, through galaxies, through magnetic fields and starlight, and finally, through us. Right now, whether you're inside or under the open sky, whether it's day or night, these particles are hitting you. Hundreds of them pass through your body every moment without your noticing. They pass through walls, oceans, and even the crust of the earth. Some come from our sun, tossed casually in solar flares and ejections. But the most mysterious ones come from farther out, from places we can barely imagine, from epochs so ancient that their origin no longer has a visible trace. Cosmic rays aren't rays at all, but particles, mostly protons, some heavier atomic nuclei, a few electrons. Most of them travel close to the speed of light, pushed by extreme events. Supernovae, exploding stars, neutron stars spinning with fury, galaxies colliding, black holes feeding. In some rare cases, we detect particles with such absurd energy that they boggle even the imagination of physics. One proton, just one, can carry as much kinetic energy as a thrown baseball. That's a single subatomic particle carrying the force of something you could hold in your hand. We've given these travelers poetic names: ultra-high energy cosmic rays, or UHECRs. They're so rare that you could wait years to detect just one hitting a square kilometer of Earth. But they do arrive. They pierce the atmosphere like tiny bullets, colliding with air molecules and causing cascades of secondary particles, which spread out and fall like sparks across hundreds of meters. And then they're gone. Gone, but not forgotten, because every one of them carries a story. Some began their journey in distant galaxies, millions of light years away. Some may have started in the jets of quasars, their launch velocity so immense it shredded matter to its core. Others may have come from gamma-ray bursts, short, savage explosions thought to be among the most energetic events in the universe. They've been traveling so long that the light from their origins may have already faded, their sources long gone, their galaxies evaporated into silence. And yet these tiny fragments of energy kept going, unstoppable, mostly unbothered by magnetic fields, though some get deflected and curved like travelers taking scenic routes. Their paths are twisted and tangled, so we rarely know exactly where they came from, but we know that they came from far, farther than the nearest stars, farther than the glow of familiar galaxies. These particles are the lone survivors of ancient violence, and they keep coming across the deepening dark. When they reach us, they arrive with no warning. They make no sound, cast no shadow. Most don't even reach the ground. They collide high in the sky and dissolve into showers of secondary particles. But our instruments catch the signs. Giant detectors, some buried under Antarctic ice, some stretched across deserts, wait for the flickers of light or traces of charged particles, marking the final moment of a journey that began eons ago. The scale is dizzying. A particle born from a distant galaxy could take tens of millions of years to reach Earth, only to disintegrate in a millisecond when it meets our atmosphere. That's a journey a billion times longer than its arrival lasts. But that's how space works. Time stretches, distances multiply, and even something so small, if persistent enough, can span a universe. Cosmic rays are also a mystery that hasn't been solved. We still don't fully know how the highest energy ones are created. Our best accelerators on Earth, massive machines like the Large Hadron Collider, can't come close to reaching the energies some of these particles carry. That means there are engines out there in the universe more powerful than anything we've yet built or conceived, launching particles across unimaginable expanses, flinging them into the dark with no guarantee of arrival. And they don't just pass through us harmlessly. In rare cases, cosmic rays can disrupt electronics on satellites, corrupt data, or even cause tiny mutations in DNA. But most of them are too small, too few, too scattered to cause real harm. They're more like cosmic whispers, barely heard but always present. There's something deeply humbling in knowing that, at any moment, your body is being brushed by particles that began their journey before humans had learned to write. That long before the Earth looked like it does now, before the continents settled or ice sheets formed, these particles were already en route, skimming past galaxies, threading through cosmic voids, weaving their way across the expanding fabric of the universe to end their journey here. Not because Earth was special, just because Earth happened to be in the way. In that sense, we are not separate from the cosmos. We are part of its circuitry. Every flash of starlight, every gravitational pull, every atomic particle is part of the same unfolding. We are hit by cosmic rays, yes, but we also emit them. Some leave Earth, launched by solar flares or by human machinery, adding our own faint signature to the galactic winds. And so the sky remains alive, even when it looks still. There are storms of light and silence drifting through it. Not just beams and photons, but particles with mass, momentum, and memory. They carry the echoes of places we've never seen, and events we may never understand. They do not stop for us, but we can listen, because every second, from all directions, the universe sends us particles that whisper of its size, its violence, its age, and somehow, almost impossibly, they arrive. Out beyond the last galaxy your eyes will ever see, past the farthest flicker of light ever to reach us, there is no edge, there is no wall, there is no end of space where the universe stops like the shore of a cosmic ocean. There is only more silence, more stars, more of something, or maybe everything just hidden beyond the veil of what we can observe. We call it the observable universe for a reason, because that's all we have, the part we can witness. A sphere of light around us, 93 billion light-years wide, created not by the universe's edge, but by time itself. The light that reaches us today is the light that had enough time to make the journey since the beginning, the moment space and time ignited in what we call the Big Bang. Everything beyond that distance is not beyond existence, just beyond reach. Those photons are still traveling, still trying, still on their way, but the universe expands faster than they can cross it. It's not that we'll never see them because they don't exist, but because the stage they're playing on is stretching even as the performance continues. In a strange, poetic twist, the farther you look, the older the universe becomes. Look deep enough, and you're not seeing stars as they are, but as they were when they were just being born. Galaxies as fuzzy little infants, barely formed, structures not yet shaped, light stretched so far by time and expansion that it sinks down into infrared, into microwaves, into echoes. What we see is a shadow play of the past, a glowing memory pressed into the fabric of space. And yet, the moment we call now keeps moving forward. With every heartbeat, light from new places is heading toward us. But in an accelerating universe, most of it will never arrive. The edge of visibility is not fixed. It's retreating, slipping away faster than we can follow. Entire galaxies that we can see today will one day vanish, not in some violent collapse, but in silence fading below the red horizon of physics, their light too stretched to ever reach us again. This means something wild. We will one day be alone, cosmically speaking. A future where the stars we now map and catalog are gone, where distant galaxies are not just invisible, but unknowable, where the universe seems smaller not because it is, but because our view is dimming, like being the last person in a fading theater, long after the crowd has left, watching the stage go dark. And still, the universe doesn't end. Space continues, maybe forever, maybe looping, maybe folding back on itself in ways our flat maps can't yet show. Some theories suggest that space could wrap around like the surface of a sphere, so that traveling far enough in a straight line could eventually bring you back to where you began. Others suggest infinite flatness, a plane stretching. forever in every direction, holding an unending sea of galaxies, most of which we'll never detect. Maybe there are other observable spheres out there, each centered on someone else, somewhere else, peering into their own slice of the cosmos. That's the quiet paradox. Your version of the universe is centered on you, not because you are the center, but because your position is where the light is arriving. Every observer, no matter where they stand, sees themselves in the middle of a different bubble of visibility. And outside that sphere, their own unknown lies waiting. What lies beyond your edge is someone else's center, and beyond that, another. We used to think the universe was small, a few stars, a few wandering planets, a dome above our heads. Then we discovered the Milky Way was a galaxy, and we were just a speck in one spiral arm. Then we found out there were other galaxies, thousands, millions, billions, now trillions, each full of stars, each star with planets, many with moons, and we mapped as far as we could. But every time we reached a new boundary, the universe responded with a whisper, "There is more, and maybe there always will be." The idea of an infinite universe is terrifying and comforting all at once. It means there is no final curtain, no wall at the edge of space where everything just stops. But it also means we will never, ever see it all. We can build better telescopes, go deeper, read the redshift, catch ancient photons, count quasars, chart microwave echoes, but the end will remain just out of reach, because maybe it doesn't exist. Maybe the universe is like a thought, always extending, never concluding, too large to hold in a single mind, too vast to paint on the wall of any planet. And if it is infinite, then it contains everything that can be. Every possible configuration of stars, every shape of galaxy, every twist of dust and light and time, maybe even alternate versions of ourselves, shaped by different physics, different histories, different paths, maybe the same particles rearranged, maybe not. But somewhere, in the deep, there is a version of the universe that we will never touch, and yet it still exists, waiting. This is what makes space so powerful. Its refusal to resolve into something simple. You can know its laws, its math, its behavior, and still feel utterly undone by it. The edge we draw around our universe is not the end of the story. It's the start of imagination. And the more we learn, the more the boundary becomes not a fence, but a question. We do not end at the edge of what we see. We end in wonder.